In this video, I'd like to provide an update for 10.5 AOS-CX VXLAN EVPN. So these are the new additions in 10.5. We now support EVPN Type 5 routes, which are IP prefix. In the past, with 10.4, we used to support Types 2 and Types 3. We also now support distributed layer 3 gateways that use symmetric integrated routing and bridging, or Symmetric IRB. This supports IPv4 unicast routing in the VXLAN overlay network. There are three use cases that we have this Symmetric IRB supported. The first is Intra-DC. The second is for Inter-DC, which is like a data center interconnect use case. And finally, we also deploy this in the campus. Next, we also support DHCP relay for the distributed layer 3 gateways here. Finally, a new VLAN client interaction feature. The main benefit of using a distributed layer 3 gateway is to optimize layer 3 network connectivity and minimize latency between virtual machines within a rack. As you can see here, with the Anycast IP 10.10.10.1 on both Rack 1 and Rack 2. Rack 1 has leaf 1A, Rack 2 has leaf 2A and 2B, with the same Anycast IP 10.1.10.1 in both racks. That means if I have a VM 10.10 that's trying to communicate with another VM 11.10 in the same rack, and the default gateways are at the top of rack, they can be routed directly without leaving the rack. And same for this Rack 2. With 10.11 that's trying to communicate with 12.10, they can communicate directly through this. So vendors can implement this distributed layer 3 gateway using either Asymmetric IRB or Symmetric IRB. Take note, AOS-CX 10.5 only supports Symmetric IRB distributed layer 3 gateways using your layer 3 VNIs, as it really scales better. Before we explain Symmetric IRB, let's start by explaining Asymmetric IRB and why is it less scalable. We have a host 1 here on the left with MAC 1 and IP 1, host 2 here on the right with MAC 2 and IP 2. So host 1 is trying to communicate with host 2, and they're on different VLANs. Host 1 is on VLAN 10, which is mapped to VNI 10. Host 2 is on VLAN 20, mapped to VNI 20. Host 1 will send to its default gateway. Source and destination IPs will be IP1, IP2. Source MAC will be host 1 MAC address. Destination MAC will be VTAP1 with VLAN 10 default gateway MAC. When he sends the traffic to VTAP1, VTAP1 will route it to the destination VNI 20. So the ingress VTAP will route it from source VNI to destination VNI. He will encapsulate it, but before encapsulating, he will actually modify. The source and destination IP is not changed, but the destination MAC is changed to MAC 2. The source MAC is also changed to VTAP1 MAC address. When VXLAN encapsulation is done, you see source IP and destination IP are the VTAP IPs. The VNI is VNI 20, which is the destination VNI. You send that traffic to VTAP2, you will receive it, you remove this encapsulation, VXLAN overhead, and forward out. Because he knows that MAC 2 is directly connected and forwarded out, but the source MAC will remain, right? So this part is not changed. You just remove this overhead. So the egress VTAP basically just bridges. It removes the VXLAN and bridge. So take note, both source and destination VLANs and VNIs need to reside on the ingress VTAP. You need to configure both routing and bridging on the ingress VTAP, but the egress VTAP only performs bridging. So why is it called asymmetric? Because the bidirectional traffic is actually asymmetric. From left to right, it's using 10 to 20. From right to left, it's using 2010. This host 2 will send to its VNI 20 gateway and route to VNI 10. So that's why it's called asymmetric, because you're not using the same path in both directions. So with this, there really is an increased MAC and upscale required on the VTAPs, because VTAP 1 will need to hold the ARP and MAC address of your destination host here, and there's additional configuration overhead because you need to configure the same VNIs and VLANs on all the VTAPs. Let's take a look at Symmetric IRB using layer 3 VNI next. We also have the host 1 that's trying to communicate with host 2 on a different VLAN, VNI. Host 1 will send to its VTAP 1 gateway, VLAN 10, gateway MAC. This ingress VTAP will actually route from VNI 10 to a layer 3 VNI. You can see the source IP and destination IP is not changed, but the inner source and destination MAC is changed. So the source is now VTAP 1 router MAC, the destination is VTAP 2 router MAC, and we do add on the VXLAN overhead on top. Source IP, destination IP are the VTAP IP. The VNI is now using the layer 3 VNI. That traffic is sent to the egress VTAP. He will receive it, decapsulate the VXLAN, and he will route to the destination VNI or VLAN. See, this top part is removed, and now he was sent to this destination MAC 2. But the source MAC is actually VTAP2's gateway MAC address. So you can see that routing is done on both the ingress and egress VTAPs. It's bidirectional. It uses symmetric paths. Symmetric meaning from the left to right is using 10 and 1020, the layer 3 VNI, 20 to exit. From right to left is 20, the middle 1020 VNI, and it exits using VNI 10. So both left to right and right to left, they both use the layer 3 VNI 1020 in the middle. So it's symmetric. VTAPs do not need to hold unnecessary ARP or MACs. So VTAP 1 does not need to hold the ARP entry of this host or the MAC address. So it's not in the MAC table, but it is in the BGP EVPN table. Another benefit is you do not need to configure the destination VLANs or VNIs on the source VTAP. So there's no need to configure VLAN 20 or VNI 20 on VTAP 1. We covered the distributed layer 3 gateway use case at the beginning of this video, but in this slide, I'd like to expand more on it. So for spine options, we really recommend the A325 as the EVPN route reflector. As you can see here, this port, we have OSPF Area 0 and AS65001. One single AS for each port. So if you have a port 2, you wanted to replicate this, port 2 would also have OSPF Area 0 with another AS number 65002. So the A325 can be used because it only has 32 ports of 40 or 100 gig. That means you can have up to 32 leaves in that fabric. If you wanted to expand, add more leaves, you basically have to change out a spine to a high port density switch. So the 8400 is recommended as your high port density spine. That is also capable of EVPN route reflector. For the leaf switches, we recommend the A325. Could be standalone, but we recommend VSX for servers that dual home. When you have a VSX switch, if the server is dual home, if one of the switch fails, the server will still have connectivity to the remaining switch. And with the distributed layer 3 gateways, when a VMV motions to a different rack, there's no need to re-up because the same default gateway IP and MAC address is used across multiple leaf switches. It is not mandatory for the same distributed gateway or subnet to be used across all racks. It's fine if you wanted to. So you have VRF-A with VLAN 10 spread across all 3 racks here because you might need to vMotion across all 3 racks. But here we have VRF-B with the 220 subnet that only exists on racks 1 and rack 2. The application does not require that same subnet in rack 3. So rack 3 requires a different subnet for VRF-B with 221 subnet. And they can route using the layer 3 VNI between the different subnets. So this distributed layer 3 gateways, we will support IPv4 DHCP relay for the distributed gateway. That DHCP relay will need to be in a default VRF as part of the underlay or reachable through a non-default VRF using option 82 sub-option 5 with 151. The previous slide I covered IBGP EVPN, but we also support eBGP EVPN within a port. We support multi-AS and dual AS. Multi-AS means the different racks are in different AS numbers, spines are in one AS number. Dual AS means all leaf switches are in another AS number compared to the spines. So most of the time, we recommend IBGP EVPN with OSPF for most of the enterprise customers, especially in a multi-port environment. But if you really wanted to, you could also use eBGP EVPN for third-party interop. So the distributed layer 3 gateway is also supported with eBGP EVPN if you wanted to. So we could use distributed gateways across different racks. If you wanted to, you could also use it across different data centers, across a wide area network in the middle, or if it's a campus environment, across the campus. So it's basically the same thing as you see here, just it's DC1, DC2 compared to rack 1 and rack 2. Your gateway IPs are distributed across the VTAPs. This will support layer 2 and layer 3 IPv4 unicast and layer 2 multicast because there's no PIM in the overlay. And we do not require VRP because the distributed gateways use any cast. For this, we still recommend A325 as the VTAPs. But just take note, the wide area network will add latency and will have lower bandwidth and might have MTU limitations compared to the intra-DC use case. If we expand this further, it's going to look like this. Right? You could have a data center with leaf and spine. In DC1 and DC2, we have the same thing, but you could have your distributed gateways spread across all 4 racks like this. Same IPs, anycast IPs on all 4 racks. And you could have your route reflectors spread across both DCs for high availability. Both data centers are in the same AS number. Just take note, there will be multiple VXLAN tunnels going across the DCs like this. So the more VTAPs you add, the more tunnels will be required across the data center. The distributed layer 3 gateway can also be deployed in the campus on the access layer. Here you see we have access 6300 VSF VTAPs and 6400 standalone chassis without VSX. Typically, these end clients in the campus, they do not dual home. You could have the default gateway spread across multiple access switches like this in building number 1. Typically, in other buildings, you can just route. So VRF A, you have 10.10.10, 10.10.11. In building 2, you have 10.10.12, 10.10.13. And you can route using the layer 3 VNI. But some devices, like the IoT devices, they need to be on the same subnet across different buildings. So you could extend the layer 2 VNI 221 across to different buildings for this IoT device. This is a distributed layer 3 gateway on the access. We also have the borders on the campus core, A325s, provide connectivity between the overlay networks and the non-overlay network. The DHCP relay could be in your edge data center, but it has to be placed into the default VRF or a non-default VRF that's not in the overlay. For the DHCP relay on the access switches, we have a DHCP server that's in the default VRF. The access VTAP will basically send the DHCP discovers through the default VRF in the underlay to the DHCP server. So the 6300 or the 6400 access VTAPs, they will advertise their loopback 0 into the underlay, and that will be reachable to the DHCP server. So you need to set your DHCP relay source interface on the access switches. DHCP option 82, sub option 5, and 151 will be sent by the VTAP to the DHCP server. You could also place the DHCP server to a non-default VRF on the underlay. For example, you have a VRF services here. This link has to be connected to the default VRF on the underlay network. So if that happens, you have connectivity from your DHCP relay source interface. Your 101.1 and 101.2 has connectivity to the DHCP server remotely through this default VRF, and the default VRF will connect to the services VRF here. Let's look at sample DHCP relay config next and packet capture. This is what you configure on your access VTAP or your leaf switch, loopback that's advertising into OSPF. We do need to modify the source interface DHCP relay when it's trying to communicate with the DHCP server remotely. These two commands are required globally. On your SVIs, which are the default gateways facing your clients, you attach your VRFs, you have your physical IP, your SVI IP, and your active gateway. This is your Anycast IP. Anycast IP and MAC address, and you have your IP helper that's pointing to the remote DHCP server that exists in the default VRF. It will be the same for multiple SVIs. So VRF2 will also point to the DHCP server through the default VRF. In the packet capture, you can see here, this access VTAP 1.3 is sending to the remote DHCP server 3.242, the DHCP discover, and it's also sending DHCP option 82, sub options 5, 11, and 151. You can see the sub option 5 is your physical SVI IP, so that the DHCP server knows this is the source subnet. And you can see in the sub option 151, we do send the VRF name. So the DHCP server, if it supports overlapping subnets, this can be used. This VRF name is sent to the DHCP server, and it must know what to do with it. So we do know that Ubuntu DHCP server supports VRFs with overlapping subnets, but Windows DHCP server does not. Let's look at some sample configs for the distributed gateways and the new VLAN client interaction feature. As I mentioned previous slide, you have your SVIs with the VRFs, unique SVI IPs, and these are your Anycast IPs on each VTAP for the distributed gateways. You have your interface VXLAN, your source tunnel source, and your VNIs and your VLAN mapping. We also have the layer 3 VNI here. So for each VRF, you only need one layer 3 VNI. You enable routing on that layer 3 VNI. So this new feature is only available on the 63 and 6400 switches to optimize resources. What happens is you still need to pre-configure all your VLANs and VNIs, but when there's no client that exists on that VLAN, the associated VTAP peers will stay down, and EVPN routes are not advertised out. This is the new command that's globally enabled. But when the first client connects into that VLAN will come up automatically, and the VTAP peers will also come up. When that happens, your EVPN routes will be advertised out. Let's say, for example, if the last client leaves that VLAN, your EVPN routes will stop being advertised and that VLAN will go down because no client exists on that VLAN. This is the new command that's enabled globally, and these are your edge colorless ports facing your end clients. So once a client authenticates, it can be placed into your desired VXLAN tunnel, depending on the VLAN ID pushed down. On this slide, I would like to compare the differences with and without this new command. Here, the first example, I have a default without this command, globally enabled. You can see I have my user VLANs 101, 102, 103. They are configured, they are attached to the VXLAN interface, and they are shown as up. And I have a port here, VLAN 2000, that's not attached to anything, that shows down without no member port. When I enable that command, what happens is you can see 101 and 103, they have no member forwarding because there are no clients attached to that VLAN. But VLAN 102 has a client connected on port 11, so that you can see that VLAN is now up compared to VLAN 2000 without any attached ports. You can see the difference. Right? There's no member port, there's nothing attached, but no member forwarding if there's no clients that are authenticated on that VLAN. So all VLANs are down with this new command. Example 2, show interface VXLAN, default without this command, all your VNIs are up and peering. With EVPN, the new command enabled, only VLAN 102 has a client and only that will be enabled with EVPN. The other VNIs 101 and 103, because there's no client connected, it will not be up. Finally, we have this show BGP L2 VPN EVPN. This is from a 6300 perspective. It's basically advertising on all three VNIs 101, 102, 103. It's advertising out. This example we have IMAT3 for the bump traffic, it's sending out that. Same for 103. But when you enable this command, because 101 and 102, there's no client attached, it's not advertising anything else. So it really helps save on resources if there are lots of VLANs without any currently attached clients.